Thank you. So my name is Marius Bjorge. I'm based in Trondheim, Norway, working on graphics researchy things. And today I'll talk about some advanced uses of pixel local storage. So this is the agenda. So first I'll cover some of the basics of pixel local storage, and then I'll go through some use cases and also introduce a new use case that I've been working on. Pixel local storage, or PLS, is a general purpose per pixel storage. It's basically the tile buffer storage that Sam previously mentioned, that we're now exposing in the fragment shader, so you can directly read and write data. And this data is automatically discarded once the tile is fully processed, so you're not wasting any external memory bandwidth when doing so. So it works by allowing the fragment shader to declare sort of a view of this PLS memory with formatting. So since this is per fragment shader, you can declare it independently between fragment shader invocations, so you can do reinterpretations between different passes. And all of this is independent of the frame buffer format. So slightly simplified, this is what the rendering pipeline looks like when you're using PLS. So you have your main memory on the left and the on-chip tile resources on the right. So there are basically two paths from the fragment shader to the tile buffer. So we have the fixed function path that goes through the blender, and the more programmable path that goes through the PLS variables and allows you to do direct and read and write accesses. So a couple of things to note is that the fragment submission order still applies, and also all the fragment tests, such as depth and stencil, they also still apply. Also, the PLS values and the colors share the same memory allocation. So if you write to one of them, you will effectively discard the other data that's there. So there are some considerations to think about. And one of the obvious use cases for PLS is deferred shading. So deferred shading is typically implemented using multiple render targets and requires a large amount of memory bandwidth. So this fits PLS perfectly, since you can treat the PLS as your typical G buffer and basically store all the G buffer properties directly on chip. So when you do your final resolve, you have all your properties available directly, and it's really efficient. Another good use for PLS is order independent transparency. So we've used PLS to implement depth peeling, where we basically ensure that fragments are shaded in sorted order. And we also implemented approximate approaches such as multi-layer alpha blending and adaptive range blending. And we presented this at SIGGRAPH last year, so recommend taking a look at that presentation for more information about how this was implemented. And as mentioned, one of the major benefits of PLS is that it allows you to change the layout of the PLS variables mid-frame. So this makes it easy to chain different techniques together. So in this diagram, you have basically chained together deferred shading with order-independent transparency. So you do your regular deferred shading with light accumulation and resolve, and then you do your transparency rendering afterwards using PLS as a OIT storage. And this works out very efficiently compared to the conventional immediate mode renderers, where this would basically not be possible without using a lot of memory bandwidth. So for a sample code and more information about how to use PLS, I recommend going to our Mali developer website and taking a look at our OpenGLES SDKs for this. So next I'll talk a bit about some of the research I've been doing around the topic of indirect lighting pipelines on mobile GPUs. So first, some of the related work on this topic. So efficient rendering with high local storage is a talk that we gave at SIGGRAPH last year about how to use the on-chip resources to do things like deferred shading and order independent transparency. Spherical harmonics irradiance volumes is something that's used to cache irradiance samples in sort of cells in a volumetric structure. It's used to accelerate global illumination. So at render time, you basically just sample this 3D volume, and the nearest points in the volume is interpolated to estimate sort of the global illumination at that particular point in the scene. Reflective shadow maps is that's basically a shadow map, but you render with multiple render targets, and you also store normals and the surface color. So you use this to generate virtual point lights that you sort of inject later on into the scene. And light propagation volumes is also very similar to spherical harmonics irradiance volumes, but instead of storing irradiance samples, you store a distribution of radiance. So the scene is first rendered from each light source into reflective shadow maps, and the texels from these reflective shadow maps are then used to represent a set of virtual point lights that you inject into these volumes, and then you propagate them through using an iterative process. But common to these approaches is that they only work on very low frequency lighting information. So getting detailed reflections is not possible. You can get some very glossy type of reflections, but not very detailed. So at ARM we have Geomerics, which have a product called Enlighten, which they will present later on. So Enlighten obviously remains the global illumination solution of choice for mobile because it's proven, it's high quality, and it works across a wide range of platforms. So this research project is completely separate. It's more of an exploration of the PLS capabilities. So the idea of this indirect lighting approach is to use a grid of probes, and the main idea is that these probes are real lit based on visibility and other properties. But instead of continuously updating reflective shadow maps as the previous approaches, all the surface properties are statically stored offline when probing the scene. And since we're updating the probes directly, there's no need to propagate the lighting information throughout the volume. We still need to generate virtual point lights, but this now becomes a very simple deferred shading operation. So with this approach, we're not only storing low-frequency lighting information, we are also storing high-frequency information, so we can use that to generate reflection maps that we can feed into our lighting engine to get, well, you can basically feed a physically based renderer with all this information to get quite nice results. So this is the high-level overview of the technique. So there are two major parts. There's an offline part and the runtime part. So the offline part probes the particular scene for indirect lighting information and stores that for later use. The runtime uses this probe data from the offline process and computes indirect lighting based on any dynamic lights that you have in your scene. And the output from the runtime is stored into irradiance volumes or a set of reflection maps if you have those mapped into the runtime. There's also a dotted line between the irradiance volume output and the runtime, and that is to support sort of multiple bounces of light, which I'll come back to later. So just to make it clear what indirect lighting is, if you consider this screenshot, it contains only the direct lighting part of the scene. So you can basically only see whatever is struck by the direct lighting from the sun. But obviously the world doesn't work that way. Light bounces around until it's completely absorbed by the environment. And here's the lighting contribution of the scene. So here we use the lighting reflected from the direct lighting plus lighting from the hemisphere. So we also use, we can also render the hemisphere into the probe relighting mechanism to get indirect lighting from the hemisphere. This is the reflection part that's generated from the runtime. This is a bit exaggerated just to sort of show how it works. You can get more crisper reflections as well, but for this particular scene it used very rough surfaces. This is a final composited image, also with reflections. Yeah, these kinds of subtle reflections that you can see at least on the teapot and also on some of the drapes there is something that adds a lot of realism to an image, which is really important. Yeah, and here's just showing the lighting information, just only, yeah, with white albedo surfaces basically. So now I'll go into the different processes, and first I'll talk a bit about the offline process. So this is basically how probing works. For every probe in the scene, you render and gather albedo, normal, and depth from all directions. Then you save this off to a bigger sort of a texture atlas that the runtime uses to do the per probe relighting. For my implementation, I've used a depth value of 1 to hint that this is not a particular surface, so that's reserved for a hemisphere. So when relighting and using depth equals 1, we add the hemisphere, basically. So there are multiple ways of actually storing this probe data. Cube maps or latitude-longitude maps can be used to store the high-frequency data, while low-frequency can be stored using second-order spherical harmonics. For low-frequency data, we also need to store coefficients for the hemisphere as well as nearby occluders to be able to correctly regenerate the lighting information in those particular probes. So there's a more visual representation of the actual data that is stored. So you have the cube maps, latitude-longitude maps, and spherical harmonics. So you can save a considerable amount of storage by just using spherical harmonics, but by only using that, you don't get any of the benefit of reflections. And also latitude-longitude has issues, at least if you do, at least when you sample from the poles of the sphere, you can run into texture warping issues. So cube maps has the best quality, but there's a consideration to take into account what basically how many probes you're using and the quality you want. So after probing a scene, we have a lot of extra information about the scene. So we can, for instance, deduce visibility between the different probes. So for each probe, we can determine which of its neighbors it can see. So if there's an occluder between two neighboring probes, we have a bit mask updated that says whether or not these two probes can see each other. And this bit mask is later used in a texture that's fed into the indirect lighting in the runtime. And this is used to avoid light leakage, which is often a problem with these kinds of approaches. We also have some special bits that say whether or not the hemisphere is visible, which is useful for avoiding extra updates that aren't affected by global lights, such as the hemisphere or sunlight. The depth information is also used to determine the bounding volume used for the local cube maps, which is used for applying the reflections in the scene. Another nice property of this information is that it can be used to reduce computations when moving or changing local lights. So if you're moving around a light in room A, we can deduce that you won't have to do any updates of any of the probes in room B. So there's basically a lot of information that we can use to limit the number of computations that's needed. So next I'll talk a bit about the runtime. So the runtime's task is to relight the probes using the lights in the scene. So the first step is obviously to determine which of the probes that you actually need to update. And this is where the probe metadata that I previously mentioned becomes really important. If a probe needs to be updated, it's pushed into a queue for further processing. And here is the per probe pipeline. And this pipeline is executed for every probe, but it's heavily batched, so we do this for several probes at the same time. And this pipeline is quite long, so the idea here is to spread this load over several frames. So not every step here is executed in the same frame. And we sort of determine which lights contribute to a particular probe by doing normal bounding volume tests, as well as using the metadata, as I mentioned previously. The third relighting of the probes uses the probe, basically the offline output, where we store their albedo, normal, and depth. And we basically do a deferred shading approach using that information. And PLS is, this is where basically PLS comes into play, because PLS is very, very useful to do this at high precision to accumulate all the lighting information per probe. Hemisphere lighting is also applied here by doing the comparison, checking whether or not depth is equal to 1. And dynamic lights is that's applied just as a normal deferred shading implementation. So you can in many cases reuse an existing lighting pipeline for this case. What's also nice is that you can get the benefit of shadow mapping and all those kinds of effects. So it works very nicely with an existing pipeline. You can also add reflectors and dynamic objects that reflect lights in a particular way and render them as normal into the relighting step. So you can have objects that change color and it will affect everything in the scene. Computing the Sverga harmonics it's basically a parallel sum operation with Sverga harmonic coefficients, and everything is run on the GPU. And this can either be implemented using compute shaders or in multiple fragment shader reduction passes. And the irradiance output from this is finally stored in two separate red, green, and blue 3D textures that we're using to later on sample when actually doing the rendering of the scene. So as mentioned, when we apply this to the scene, we do a simple 3D texture lookup using the world space position. And this, using this, we get the spherical harmonics coefficients, and then we do a lookup based on the direction that we want to get the color of, sort of. So the result from the probe relighting can also be stored into cube maps, as mentioned. And this is useful to support dynamic reflections. So to smoothly transition between smooth and rough surfaces, we also need to generate MIP maps. GL-generate MIP maps was found to produce good enough results. Proper cube map filtering will probably be much better, but it's just too expensive for the runtime, at least on mobile. The idea here is also to, I haven't actually implemented that, but a better way is to spread this MIP-map generation across several frames as well, because generating MIP maps of cube maps is quite expensive, since you have to generate MIP maps for every face of the cube. So you basically get 6 times the number of MIPs that you need to compute. So spreading the load can be quite important. Multiple bounces is also supported by temporarily filtering the irradiance volume into the runtime. So here we have a single bounce lighting and multiple bounces. So you get a more clean looking lighting. So for future work, move everything to compute as well. Not only use the compute shaders for doing spherical harmonics parallel reductions, but also doing the actual shading using compute shaders. Another idea is to map things into an octave representation to have different levels of detail. Another idea is that we can use the metadata as sort of occlusion culling, because we have a lot of information there, and can easily deduce whether or not things are visible from particular viewpoints. Yeah, that was it, I think. Any questions?
Does anybody have any questions for Marius? I guess no. Okay. I guess that makes yours the most perfect talk so far. So yeah, thanks so much to Marius. Great stuff.